We're going to talk about polar form or trig form of complex numbers, just to return to our study of trigonometry. Uh, we can take an imaginary number of the form a plus bi, and we can actually plot it. Just pretend it's the point AB, and it's in rectangular coordinates. We call this the real axes, and this the imaginary axes instead of x and y, but we follow all the same Cartesian conventions. Of course, we go over A, up B, and for what we'll see in the next problem set, it's often convenient to rewrite this in terms of r and theta using polar coordinates. R is the distance from the origin to the point, and theta is a counterclockwise standard trigonometric angle starting at the positive real axes. And we have these right triangle relationships. Cosine theta is adjacent over hypotenuse, A over R. Sine theta is opposite over hypotenuse, B over R. Of course, you can solve for A, R cos theta. B is R sine theta. These are familiar polar coordinate transformations. We also have R squared equals A squared plus B squared, and tan theta is equal to B over A. That's a convenient relationship as well. We can take an imaginary number A plus BI and rewrite it as A is our cos theta, B is our sine theta, factor R out. R times cos theta plus I sine theta is what's called polar or trigonometric form of a complex number. All we're going to do in this exercise is take a bunch of these and rewrite them like this. So the goal is, given A and B, figure out R and theta, plug into this template right here. It's just, we just want you to familiarize yourself with that process. Next problem set, we'll learn about something called de Moivre's theorem. We'll learn why it's so convenient to take this and put it in this form for doing basic operations on imaginary numbers. Well, we're going to start with the number 2. 2 is equal to 2 plus 0i, and you can represent that with the point 2, 0. Where's the point 2, 0 located? It's right here. And you can see r equals 2, theta is 0 degrees. We'll work in degrees here for simplicity's sake, 0 degrees. And so the r cosine, we're going to plug into this format. We have r is equal to 2 cosine 0 plus I sine 0. Okay, and 2i is the point 0 plus 2i, which is 0, 2. That's located up here. And it's clear from that that r equals 2. Theta is 90 degrees. We're all the way up here at 90 degrees. And so we have 2 times cosine 90 plus I sine 90. Let's move this down a little bit. 3 negative 2i. Negative 2i, that's 0 minus 2i, which is the point 0, negative 2. That's down here. R equals 2, theta is 270. We're coming all the way around here. And so we have 2 times cosine 270 plus I sine 270. And then we'll bring problem number 4 over here front and center. Suppose we have the point negative 2. Negative 2 is negative 2 plus 0i, which is negative 2, 0. It's right here. Okay, so r is 2, theta is equal to 180. You can follow the convention, by the way, always keeping R positive, and then theta adjusts appropriately. We get over here by having theta equals 180. In basic polar coordinate theory, you could have theta be 0, and then R equals -2 would take you back here. So this could also be written just for informational purposes. R equals -2, theta equals 0. Start here and walk backwards to here. And that would be appropriate. That would be perfectly correct, mathematically speaking. And so we have 2 times cosine 180 plus I sine 180. Okay. Now let's make it a little more complicated. Let's suppose we have 5 minus 5i. Clear a little bit of space here. And that's our real, that's our imaginary axes. 5 minus 5i is 0.5, -5. So we want to go over 5, down 5. And just by symmetry here, you can tell this is 45 degrees. Okay, so R is going to be square root 5 squared plus -5 squared. That's square root of 50, which is 5 square root of 2. And theta is going to be, we really have 2 choices here. 315 degrees or -45 degrees. Take your pick, doesn't matter. You can follow the positive convention or the negative convention, either one. I'll stick with the positive for no particular reason. And so we have 5 radical 2 cosine 315 plus I sine 315. Okay, if we were in another quadrant, of course, over here, you could add 45 to 180. If you were up here, you could subtract 45 from 180. And just doing that by inspection, if these 2 numbers are equal in absolute value. So here's another example, not quite so obvious. -3 plus 4i, which is a point -3, 4. If we plot this, real, imaginary. Okay, you want to go left 3, up 4. So we are right here. You can call this angle alpha. It's a reference angle, really. And you can make a right triangle here. This is 3, this is 4. And it turns out alpha is equal to arctangent 4 over 3. Okay, this is just a simple acute triangle. We're not interested in positives or negatives. We simply want to find that angle. This ends up being about 58 degrees if you work it out. I believe it's 58 degrees if you find the arctangent of that. And of course, we want, this is the angle theta. Theta is equal to 180 minus 58 degrees, which is 122 degrees, rounded to the nearest degree. Of course, if this triangle were in the third quadrant, we would add to 180, and if it was here, you can do the negative or subtract from 360 convention. Either way, and so we have r is equal to square root -3 squared plus 4 squared, which is square root 9 plus 16, which is square root of 25, which is 5. This is a 3, 4, 5 triangle. And so the polar form is 5 cosine 122 plus I sine 122. You can check this. Just evaluate this on a calculator, quite simply put. Evaluate this, multiply by 5, you'll end up with approximately -3. Evaluate this, multiply by 5, you should end up with approximately 4. It won't be exact because we rounded this off. This is some strange irrational number, but that's good enough to check. So you should be, either -2.99 or -3.01, and this should be close to 4, a little bit over, a little bit under. So, okay, that's all we're doing for this section. We're just familiarizing yourself with this. Polar coordinates in its own right is pretty important. Imaginary numbers important. Polar coordinates, you'll see polar coordinates in Calculus 2. You'll see polar coordinates in Calculus 3. Possibly in differential equations. Definitely if you take a course called Engineering Dynamics or Tech Dynamics, you see polar coordinates. A lot of very interesting mechanics problems that have to do with rotation. Things that are best expressed, motion having to do with rotation. For instance, a camshaft in an engine spins around, makes the piston go up and down. Anything to do with rotation is going to involve polar coordinates. As a proof, if you have a central force system, like for instance the sun and the earth, and the gravitational force between the two is inversely proportional to the square of the distance, Isaac Newton actually proved that the elliptical orbit, that the orbit is an ellipse. The proof actually involves polar coordinates. So this permeates STEM. You'll see it quite a bit. So that's all for this video.